Okay, inheritance part 3. This video actually just goes through the chi-square test if you're needing assistance with that. All right, the chi-square test. Typically when you cross two heterozygous individuals in a dihybrid cross, you would see a probability of 9:3 to 3:1 ratio for their phenotypes. Again, that's just a probability. To determine whether the differences between the expected numbers of each genotype and the observable numbers are due to chance or something unexpected, we can use the chi-square test. This statistical test allows for the comparison of the observed and the expected results to see if there's a significant difference between them. To carry out the chi-square test, you need the following information. You would need to have the observed numbers for each genotype, the expected ratio and the expected numbers for each genotype, the difference between the observed and the expected values, the square of the difference. That square of the difference gets rid of any negative numbers that might be present. The square of the difference divided by the expected value. And then the value of the chi-squared will be the sum of all the previous bullet points. So depending on how many genotypes that you're looking at, you would add them all up together. Okay, let's take a look at what this means. Let's say we have 144 offspring. We know our phenotypes: purple stems with cut leaves, purple stems, potato leaves, green stems with cut leaves, or green stems with potato leaves. To get the observed number, you'd physically would have to go through and count how many there were for each one of those phenotypes. Typically, again, remember in a dihybrid, you would have a ratio of 9:3 to 3:1. However, we can look at the expected number. To get the expected number, we have to do a little calculation. The expected number is going to be the expected ratio divided by the possible number of offspring times the total number of offspring. So I have listed here the 4 different phenotypes. These 4 phenotypes match the phenotypes across the top of our chart. The expected ratio, remember we said there's a 9:3 to 3:1 ratio. That ratio is based on 16, because in a dihybrid you have 16 possibilities. So 9 out of 16, 3 out of 16, 3 out of 16, or 1 out of 16. That's going to give you the little percent for each one of these phenotypes. And then you would take that and multiply it by 144 because there's 144 offspring in this example. That's where we're getting our expected number. And you'll notice those are the numbers that are in the chart. Then you're going to take the difference between the observed minus the expected. And that's where we're getting our next set of numbers, data. And then we square that value. Again, squaring it's going to get rid of any negatives, because negative times negative is a positive. So this gives us all positive values. Once you have squared the values, you then divide that again by the expected number. So this 25 is going to be divided by your 81. Okay, that's where you're getting this 0.31. And you do that for each data set. You would then take each one of these and add them up. When you see this symbol, this means the sum of. So as you've calculated each one of these, the sum of means you're going to add them all up together. And when we add them, we get 0.79. So what does this mean for us? What do we have to relate this to? All right, once you have your chi-square value, we now need to figure out what does that value mean. To do so, we must look at the table that relates the chi-square values to probabilities. This table is the one you're using, and this is given to you. You're not calculating these. You're going to have to use it though. The table is going to give us the probability that the differences between our expected and observed results are due to chance or not. In biological experiments, a probability of 0.05 is usually critical. So this is where we would use the values under the 0.05. We're using these values. If our chi-square value represents a probability of 0.05 or larger, then we could be fairly certain that the difference between our observed and expected results is due to chance. The difference, therefore, would not be significant. If the probability is smaller, then it's likely that the difference is significant, and consider what else could have possibly gone wrong with the cross, with the offspring being produced. In addition to looking at if the value is greater than or less than to look at the probabilities, we also need to look at the degree of freedom in the results. This value takes into account the number of comparisons made. To work out the number of degrees of freedom, calculate the number of classes, the class data minus 1. Class data meaning the possible sets of phenotypes. In our example, we had 4 possible phenotypes. These were our 4 different phenotypes. So we would have 4 minus 1, which would give us a degree of freedom of 3. Now we know the degree of freedom. We can now look at the table to determine if the results show a significant deviation from what was expected. The numbers in the table are the chi-square values. Look at the third row. This is the third row, this third degree of freedom, because we've determined that our degree of freedom was 3. And then find the chi-square value underneath the 0.05. So go across, here's the 0.05. So we come to 7.82. The calculated value for our chi-square was 0.79. This is a much smaller value than what's in the table. It represents more of a 1 in 10, which would be 0.1. So the difference in the results is just due to chance. The difference between the observed and the expected values is due to chance. There's not a significant difference. When this occurs, this is going to support something known as the null hypothesis. The null hypothesis states there is no difference between your observed and expected results. The difference is due strictly to chance. Okay, here's a practice problem for you to try. You could go through this practice problem and I'll have the solution for you so you can see if you're on the right track for this.